Hello everyone, welcome back to Infinite Insights. Today we're going to cover some calculus basics. In particular, we're talking about differentiation from first principles. This is a concept that is often skimmed over in classes but is foundational to differential calculus. Learning about differentiation from first principles and the difference quotient will give you a good base understanding of what rates of change and derivatives are about and how they really work. To understand rates of change and to differentiate from first principles, we have to go back to the basics. Now, the first basic concept is that of gradient of a straight line, the simple case. The gradient of a function represents how fast the function is changing at that point. Here in Desmos, I have a simple straight line graph, f of x equals x. For this line, the gradient is the amount that y changes when x changes by 1 unit. Because this is a simple straight line case, all we need to calculate the gradient of this line are the x and y coordinates of any 2 points on the line. So over here you have the green point and the purple point. This is parameter p, which I've used in this green point and this purple point, and I have made this purple point a distance h away from the green point by defining this another parameter h, which is the separation horizontally between these 2 points. And since this is a straight line which has a constant gradient, we can choose any 2 points on this line, and it does not matter which 2 points we choose, we'll get the same value for the gradient over here. Now, to calculate the gradient, we do rise over run, and you're likely familiar with this formula already from graphing. As we move from the first point to the second point, the rise is a change in the y value and the run is a change in the x value. Let's call this point A and let's call this point B. So the green point is A, the purple point is B. Now I can draw a line like this. If I take the y value of the green point, let's say y equals A dot y. This means take the y coordinate that's stored in A. Now let's draw a vertical line like this, which makes use of the x coordinate in the purple point. So x equals to b dot x. And now you can see we have formed this triangle between the red, purple and the green lines. So over here, this purple line, this segment is a change in y, and this green segment is a change in x. So to calculate the gradient, we do change in y over change in x. Or you could say the gradient is the rise over the run. Now to find the rise, we take the y coordinate of this point and subtract it from that of this point in order to get the length of this purple segment over here. This purple segment is a change in y. So we will take the y coordinate of b minus the y coordinate of a. And for the run, we're going to do something similar. We're going to take the x coordinate of b and subtract it from the x coordinate of a. And we see that the gradient is equal to 1 as expected, because this is f of x equals to x, the simplest case for a straight line, and it has a coefficient of 1. Now that we understand the gradient of a straight line, we're ready to extend this concept to curves in general. Just as we could calculate the gradient of the straight line in the previous example, we can also calculate the gradient between any 2 points on a curve. So these 2 purple points here are the points through which we draw a straight line, and then we calculate the gradient of this line, because right now we don't really know how to calculate the gradient of a curve. So we are taking these 2 points and forming a line between them so that we can calculate the gradient of the line, and that is going to be an approximation of what the gradient of the curve might look like at that point. The line that is formed by connecting these 2 points on a curve is called a secant line. Again, to calculate the gradient of this curve, we just need the x and y coordinates of any 2 points on the curve. But unlike last time, the gradient is not constant this time, and its value is going to depend on where we place our 2 points. As you can see, as I move one of the points, the line changes, and our gradient here is also changing. Sometimes it's positive, sometimes it's negative, and sometimes it could be 0. So over here, this is sine x plus 0.3x. We have an up and down caused by the sine x part inside f of x. Here we have 2 points, a comma f of a plus h comma f of a plus h, and the h again is the distance horizontally between these two purple points. And this red line is the secant line. M is the gradient. We multiply by x minus a and add f of a. It might be more familiar if I write it in this form. So this is the form y minus y1 equals mx minus x1. And now the manner which we calculate the gradient here. So this is basically the same thing but written in a functional notation. So just now we wrote it using the coordinates. But this is the same thing. This is just rise over run. So here f of a plus h is just the y coordinate of the second point, and f of a is the y coordinate of the first point. So just like before, we're calculating the rise, and here the run. So if we calculate the run, it's a plus h for the x coordinate of the second point, and a for the x coordinate of the first point. So that's what it actually looks like here. So this might be clearer to understand. And basically what's happening at the bottom is a plus h minus a is the same as h. Finally, let us discuss the significance of difference quotient. The difference quotient is an expression which can be used to estimate the gradient of a curve at a given point. The approximation of derivatives using the difference quotient is used in certain methods for numerically solving differential equations. The difference quotient is also used in the definition of a derivative, which I might cover on this channel at a later date. Difference quotient is a measure of the average rate of change of a function over an interval. So over here in the Desmos graph, we have this interval 2, 4, and let's say we want to calculate what is the average rate of change. So just ignoring all the curve part, just looking at this point and this point. We draw a line through it, just like the previous example, and calculate the gradient of that line. Since we know how to calculate the gradient of a line, that's not a problem. And earlier in secant line example, we also looked at an expression for the gradient of a secant line, and the difference quotient looks very similar to that first expression, but this time we generalize to any function of x. Here I'm using a function f of x equals the square root of x, and similarly we're using a parameter for our points, and again it is separated a horizontal distance h away between our 2 points, and similar to previously, we are calculating the gradient. Let us draw a secant line to visualize this gradient. So just like before, we're going to do y minus y1 equals m x minus x1. y1 is the y coordinate and x1 is the x coordinate. So y1 is going to be p dot y and x1 is going to be p dot x. Now we have a secant line that connects these 2 points, and it's actually really close to the gradient of the curve. But what happens if we try to make h even smaller? These 2 points come closer together, and it's starting to look like a tangent line. The gradient of the secant line is becoming more and more of a better approximation of the gradient of the curve at that point. And this approximation gets better and better as h approaches 0. And this is essentially what the difference quotient means. We are trying to get an approximation as close as possible of what the gradient of this curve is by keeping a very small value for h and then calculating the gradient using our first principles. So this is what is called first principles. We are using the standard gradient formula. Let's also write an expression for the generalized difference quotient for any function. So the difference quotient is going to be change in y over change in x, f of x plus h minus f of x. Because our 2 points are separated by horizontal distance h, this is the y value of the second, this is the y value of the first. The x value of the second minus the x value of the first goes in the denominator. So x plus h minus x. And this we know it simplifies to just h. And now we get this new curve, which is actually an approximation of what the gradient of the black curve will look like. So you could say that the red curve is an approximation of the derivative of the black curve. So guys, in this video you've learned about the difference quotient in calculus and how its concept has been built up from the basics. I hope this video has helped improve your understanding. Thank you for watching. I'll see you guys next time.